Hello and welcome to MMI 701, the online version of the course, Multimedia Signal Processing. In this video, we are going to talk about Z transforms. Now, Z transforms was first introduced by Lotfi Aliasgarzadeh and John Ragazzini in the early 1950s. For those of you who don't know, the first name I gave, Lotfi Aliasgarzadeh, he's an Azeri Turk. He was an Azeri Turk who died kind of recently, and he was posthumously given a medal, a state medal, by that country, and being designated as a national hero because of his contributions to science and engineering. So he not only introduced the Z transform, but he also introduced fuzzy logic and fuzzy sets. So it is a very important contribution that he did during his lifetime to our occupation and our domain. So direct Z transform, it is kind of like a simple concept. You just multiply each sample of your signal by some Z, some complex number Z to the power minus n, and sum all of that up. So although we have n equals to 0 as our lower bound here, it can start from minus infinity as well. So there's nothing that stops you from writing your bounds from minus infinity. So that's just an example. All right, so as for any series, as this is also a series, z to the power minus 1 has to be bounded for the series to converge. Otherwise, you're not going to have a convergent series. So, region of convergence is defined as the region for which this series converges. So, let's give an example. What is the region of convergence for x of z equals to 1 plus 2z to the power minus 1 plus 7z to the power minus 2 plus 9z to the power minus 3? And then the question is, well, we can pose the same question in two ways. Where does this expression converge? Or we can alternatively pose the same question as, okay, so where does it diverge? Now the second question is easier perhaps to answer. It converges everywhere except z to the z equals to 0, because 1 over 0 will make the series diverge. So it's going to diverge at z equals to 0, which means the region of convergence is everywhere but 0. Everywhere except z equals to 0. Okay, so this is the region of convergence. By the way, when I was a student of signal processing, one of the things which kind of baffled me a lot was region of convergence. I mean, as a term, it is kind of strange, convoluted. What is region of convergence? Now, when you think about it, region of convergence means the values of z for which this expression converges. So it's kind of simple. Just try to think about the meanings of these terms. It all makes sense when you do that. Okay, so let's have a look at a second example. So what is the region of convergence for the z transform of xn equals to 1 over 2 to the power n u of n? If you remember from last week, u of n is the unit step function, sorry, unit step sequence, sorry. This is the Yep. Unit step sequence or unit step signal, if you think about that as a discrete time signal. All right, so let's write the direct Z transform then. X of Z is equal to n from 0 to infinity. That is given to us, that information is given to us by u of n, that is all values of u of n when n is greater than 0, greater than or equal to 0 is non-zero, it's 1, otherwise it's 0, which means we have the bounds n from 0 to infinity. And let's write these direct Z transform 1 over 2 to the power n and Z to the power minus n, which is basically, we can just put these two terms together and we're going to have n from 0 to infinity 1 over 2 Z to the power minus 1 to the power n. Now here's a little reminder for you, a little note to remind you about where series of this type converges. So I'm going to write that little note right here. Note: if you have a series which looks like this, a to the power n, this is going to be converging to 1 over 1 minus alpha, 1 minus a, if and only if absolute value a is less than 1. Otherwise, it's not going to converge, which means a should be the absolute value of a should be less than 1. Okay, so based on this little note, so let me just make this a little bigger for you to see it clearer. Okay, that's good. So let's continue where we left off in here. So X of Z then will converge if and only if 1 over 2 Z to the power minus 1 is less than 1, or equivalently, region of convergence of this Z transform, the series, is 1 over 2 Z to the power minus 1, absolute, is less than 1, or equivalently, Z is greater than 1 over 2. Absolute value of Z. Now we talked about absolute value of Z. Okay, so then you may be asking, what is Z? Now we haven't defined Z. I just told you that it's a complex number. Well, as a matter of fact, it can be any complex number, which can be represented as in here. Okay, Z equals to r e to the power j theta, which is equal to r cosine theta plus jr sine theta. Now, this is all good, and that comes from basically the definition of e to the power j theta. Just as a little reminder, this is cosine theta plus j sine theta. Okay, so this is our complex exponential. Now, theta is an angle, a phase term, and r is the magnitude of z. Now, if you want to draw it in polar form, then we can just put it here. Let's say I'm just going to put a little square here just to represent this number. Okay, and the x-axis, which is the projection of this into the in real numbers, space of real numbers, it is cosine theta, sorry, r cosine theta, and the imaginary part is r sine theta. Okay, so we have the imaginary axis and the real axis. So this is the real axis and this is the imaginary axis, and the angle, this angle is theta. Okay, so this is z. And one additional thing that we know about e to the power j theta is that its magnitude is 1. Okay, because it's cosine squared theta plus sine squared theta, which is 1 anyway. So for convergence, we want to have the absolute value of x of z to be bounded. So let me just write it down. For convergence, we want absolute value of x of z to be bounded, to be less than infinity. So we don't want it to diverge. And let's write it down then. Absolute value of z, we're going to write the direct z transform for any x of n. And we're going to use both lower and upper bounds as minus and plus infinity, x of n, r to the power minus n, e to the power minus j and theta. Now from triangle inequality, from triangle inequality, we can just write it down as the upper bound for this sum is x of n, r to the power minus n, e to the power minus j and theta absolute. Now here's the thing. We know that, let me make this a little bigger. We know that this complex exponential is, the absolute value of this complex exponential is equal to 1, which means we would want this first part to be bounded. Okay, so that is good. Now we know something about this. So that is going to mean something. That's going to mean if x of n r to the power minus n, so there's a little typo in here, I need to change this. So this has got to be not n, but minus n, and same goes for this. Okay, so r to the power minus n is absolutely summable. That is, if this expression holds, if this relation holds, this inequality, then the series is going to converge. So let's write this down to get some information about where the region of convergence is for a general signal. So let's go ahead. What more can we extract from this? Okay, so let's write it down. We would want to write our absolute sum, x of n r to the power minus n absolute equals to. So let's write the terms on the right hand side of time origin and left hand side of time origin. So we're going to have n from minus infinity to minus 1 x of n r to the power minus n plus values including 0, n from 0 to infinity, x of n r to the power minus n, absolute value. And we can obviously change the index of summation from n to minus n if you wanted to, which is going to give us n from 1 to infinity, x of minus n r to the power n this time, plus n from 0 to, the rest is the same, n from 0 to absolute x of n r to the power minus n, which is what we already knew. Now let's also make this a little bigger. Okay, so let's think. If any of these two parts of this transform, so let's call this 1 and let's call this 2 if you like. So if any one of these parts of this series diverges, the whole series is going to diverge. The whole sum is going to diverge. So well, that's pretty much the only condition. So what do we know? First of all, given that x of n will be bounded, we haven't defined it as such, but let's say it's bounded. The first term, okay, will converge if r is less than some r1. We don't know which r1, doesn't matter that at the moment because we don't have x of n, so it's not our worry right now. We just know that the first part is going to converge if r is less than r1, because now we have elements with negative time indices for x of n and a positive exponent for r. Okay, and 2 will converge. That's something that we already found out a moment ago in our example, if r is greater than r2, which means based on these two findings, region of convergence is r2 less than r less than r1. So this is our region of convergence, a general region of convergence for a general signal, which is non-causal because it has terms on the left-hand side of the time origin as well as the right-hand side. So it's not anti-causal. It's two-sided, and the region of convergence is a ring. If you wanted to plot it in the real and imaginary axis, so if you want to plot it in the plane, which includes complex numbers, the region of convergence will be values of r which are greater than r2 and less than r1, which means we have a ring which is the region of convergence for the series. Now, there's a little kind of cheeky question. Not so cheeky because it is something which can happen in real life. What happens if R1 is less than R2? So it's kind of like a dumb question, if you like, but let's write the answer to that as well. So if R1 is less than R2, the series, or the sum rather, not the series, the sum will diverge. So this is important. Now, whether or not this is going to happen in real life will depend on the signal that you have. All right, so let's give some examples to understand this concept a little bit better. So here is our first example. x1 of n is equal to a to the power n u of n. Now let's write the Z transform by using direct Z transform. Let's call this x1 of z, if you like, is equal to, and from 0 to infinity, a to the power n, z to the power minus n, which is equal to, and from 0 to infinity, a z to the power minus 1 to the power n, in exactly the same way that we did before, and that is going to converge to this value when is it going to converge? It's going to converge when a z to the power minus 1 absolute is less than 1, which means the region of convergence is absolute value of z greater than absolute value of a. So this is our region of convergence. That's good. So then the question is, what kind of a signal is this? Is it causal or non-causal? We know that this is a causal signal because on the negative side of the time origin, n equals to 0, all values of the signal are 0, which means we have a causal signal. Now, if you wanted to draw the region of convergence for this signal, we would have, let's call this the unit circle, and we would then have a circle with radius a, right? And we would want our values of z to be outside. So that means the region of convergence will be here. Okay, so this would be our region of convergence then. Outside the circle, which has a radius a. Well, obviously a can be greater than 1, it doesn't matter, I mean, then it's going to change the region of convergence to a slightly, outside of a slightly larger circle. Now let's have a look at this signal, which is kind of like a very similar signal. Not so much though. So there's a little typo. I would need to change this to 2. So this is the second signal, x2. let's have a look at this. Is this a causal signal or a non-causal signal, do you think? I'm just gonna give you a moment to think. So this is our signal, x2 of n. Now, since there is a time reversal here, we have a non-causal signal. So, non-causal. Okay, so the other one was causal, by the way. Okay, so what is the signal then? So let's write the signal. So x2 of n is equal to 0 when n is greater than or equal to 0, and minus a to the power n when n is less than 0. So let's just write the Z transform using direct Z transform. X of Z is equal to, we're just going to multiply each value by Z to the power minus n and sum. So n from minus infinity to minus 1 this time because of the time reversed unit step signal. We will have a to the power n, and we have a minus here, sorry, a to the power n, z to the power minus n, which is equal to minus, just changing the sign of the index. So it's going to be n from 1 to infinity, a to the power minus n, z to the power n, which is equal to n from 1 to infinity, a to the power minus 1, z to the power n, and this is only going to converge to what? So it's going to converge to 1 over, so it's going to converge to this, a to the power minus 1 z over 1 minus a to the power minus 1 z, which is equal to, again, 1 over 1 minus a to the power, a z to the power minus 1. So, and what is the region of convergence then? The region of convergence is, so this is going to converge if and only if the absolute value of a to the power minus 1z is less than 1. Or, yeah, the region of convergence is z less than a. Absolute value of z less than a. Absolute value of a. Now here is an interesting, okay, so let's also draw the region of convergence here. So we have a circle of radius a, and inside that circle is our region of convergence. So this is the region of convergence. Now you can see that these two regions of convergence are exact opposites of each other. But there is this interesting fact, however, and it's going to become clear when you look at these two things. I'm just going to put it with a, perhaps a different color. I don't know. So let me just select the yellow. So this and this have the same expression. So Z transform of x1 of x1 and x2 are the same. So again, Z transform is the same for both signals, which are quite different. Let that sink in. You have very different signals, and their Z transform is the same. That means Z transform by itself is not unique. Well, you need to specify the region of convergence in order to make it unique. And one additional result is causal signals have regions of convergence outside the unit circle, and non-causal signals have regions of convergence inside the unit circle. So this is also another finding from this little example. And these are very important results. So I'm just going to put a little star, if you like, for you to remember. Okay, so let's have a look at regions of convergence of different types of signals. As you know, we have finite length signals and infinite length signals. There may be different types of finite length signals and infinite length signals as well, depending on whether or not they're single-sided or two-sided. So let's consider the causal finite length signal then. So that signal is, you may just have to remember it, but let's write it here. That is x of n is not equal to 0 for a finite time support. Okay, for this type of a signal, region of convergence is everywhere except z equals to 0. And you may remember from the first example that this is indeed the case. So a non-causal signal or anti-causal signal, that is a signal which is not equal to 0 for another range minus n less than 0. So this is an anti-causal signal because it only has values to the left of the time origin. So in this case, for this kind of a signal, is everywhere except z equals to infinity. Okay, so a two-sided signal. That is a signal where x of n is not equal to 0 for some region minus m less than n less than capital N. So this is our two-sided signal where m and n are both positive. So in this case, we can write this kind of a signal as the sum of a causal and an anti-causal signal in different ranges, which means the region of convergence is everywhere except z equals to 0 and z equals to infinity. So far so good. So we have seen finite length signals and different types of finite length signals, causal, anti-causal, or non-causal, and two-sided signals. And we have specified the regions of convergence without even doing anything else, which is nice. Now for infinite length signals, for a causal infinite length signal, I'm not going to write the definitions anymore for causal signals. Now we're just going to put capital N to infinity. let capital N to become infinity, to have an infinite length signal for an infinite length causal signal. And I'm just going to write the region of convergence. Region of convergence for this type of a signal is absolute value of Z greater than some R1, let's call this R1. And for a non-causal signal, the region of convergence is Z less than some R2. And for a two-sided signal, which is a combination of these two signals, the region of convergence is Z greater than R1 and less than R2. So this is the region of convergence for a two-sided infinite length signal.